I think we in the middle of the Riemann zeta function. We have done the two things: the summation definition and actual thing, and then the related to the Dirichlet, another Dirichlet series. So that extend the domain for z to z greater than 0. And also show that the summation definition is the same as the integral representation, right? And then there's this refraction formula, but there is require a little bit of work. I don't know whether we. I mean, there's a quick, quick motivation to introduce a refraction formula because it's related to one of the greatest unsolved math mystery. So let's see. The first thing is to actually get to the form of the refraction formula that is in equation 13.67. That's basically that would extend the domain to the whole complex plane. So the zeta function would then be defined for the whole complex plane. But to get to that, there's a few steps to do that. First is to extend, to basically consider this this integral over that the contour that we introduced for the gamma function. Basically now we consider this the integration. I think this is in the t plane because now the zeta function over there. Zeta function is defined by this integral. Let's see. The last time we showed that this is equivalent to the summation for z greater than 1. Right. And now we try to extend the domain for the theta function. So at first it's both the summation and the integral defined for z greater than 1. So we have that. But with the Dirichlet series, which is quite simple, you extend it all the way back to 0. So we will see, imagine you see, right? And now to extend further, we are considering the integral. There's no equation here in it. Just describe it in this I sub A, I sub B. So basically, consider this integral. Yeah, it's either t, right? Just write it. Either the t, not either. Yeah. Yes. So now we integrate this. It's a different complex plane. This is a z plane for the domain of this theta function. But for the integral, now we consider this integral that we did that for the gamma function. So there's because of this t to the z, right? So at 0 there's a branch point. So there's a branch cut at the real t. So the integral we define is going around here. At first we can do the trick that introduce a little circle. But, later we'll just get rid of that. And so this is defined as in the textbook called I sub. This is I sub A, and this is I sub B, I suppose. So this I sub A is obviously the same as this one because you're integrating close to 0 to infinity, right? And then the contribution around this little circle is 0 if z is greater than 1. Will z is greater than 1. But later on, we'll just deform the contour to make the analytic continuation. Right. So now the I sub b is from infinity. It's just that there is the no. It's I mix up that. Yeah. Text for actually I sub a is here. I sub a is infinity to 0 to epsilon, not to epsilon. I sub b is epsilon to infinity. So I sub a, because of the opposite sign, is just minus theta z. And the phase angle is chosen to be 0 here. So the phase angle for this the t complex t, this t is this is real t, right? This is real t, imaginary t. So this is along this line is the t is absolute t e to the 0. Along this line is t is absolute t e to the 2 pi. Right. So that will for I sub b, because your t has a phase e to the minus t e to the 2 pi. So they introduce a phase up to here because at absolute t and t, both t and absolute t is greater than 0. That doesn't matter, right? And so this integrate from 0 to here, 0 to infinity will have the same as the zeta function except a phase, which is introduced by this e to the 2 pi multiplied by the power c minus 1. So it's so you have this write out explicitly. See, epsilon is infinity. Later on, just let the epsilon goes to 0, and then this absolute t is just like t, but because it defined the integral from 0 to infinity for positive t. So it's e to the z minus 1. And then you have the phase e to the 2 pi z minus 1. And the rest doesn't matter. This is not the multi-value, the rest. Okay. And what is I? Sorry. It's I. Right. And so the two factor, two terms, the second term doesn't matter. It says e to the 2 pi I, which is just 1. So you just make a phase. So it's just e to the 2 pi I times z. Right. And then the rest is just the zeta function. Okay. What's that? This IB or IB or IB, yeah. I sub B, yeah. Okay, so we do this integral and call this contour C to I. This integral I defined as this contour integral C t to the C minus 1 dt to the t minus 1 is equals to combine the two is e to the 2 pi I z minus 1. Let's see. If you do this contour integral, you introduce this factor, the proportional to the Riemann zeta function by this factor. Okay, and now the next trick is to extend for this is up to here. It's at first it's defined by z is greater than 1, but now for z is we want to actually extend it to z less than 0. So z will be the real z. We want to extend real z less than 0, right? And the idea is that now this little circle will not be 0, but it doesn't matter. We deform it, right? And we want to deform it and actually close it. So want to close it and deform it. The deformation doesn't matter as long as it doesn't hit any pole of the integram. So this deformation is just to avoid this branch point, because this little circle contribution will no longer be 0. But when you deform it, you still define it as the zeta function. Effectively, this is an analytic continuation of zeta z, because when you deform it and you're not hitting any pole, then the function is continuous. You just continuously define this function to the different z domain, so extend it all the way to other part of the compact z plane, and we actually want to extend all the way to z less than 0, right? And now basically you can say you deform it, or you can just whatever you like. This I, but it's still this I sub a I sub b is still close to define this strict part is just start from close to 0, right? But the idea is you want to figure out the pole of this domain, the integram. You can see their poles, right? What are the poles from this one? The denominator goes 0, right? So e to the t equals to 1. Then what is t? T0 is 1, yeah, right. But 0 and 2 pi I plus or minus 2 pi I, 4 pi I, etc. Right? So you have the 0 doesn't matter because we are avoiding that anyway. So we don't want the contour to hit say 2 pi I and minus 2 pi I and so on. Yeah, 4 pi I minus 4 pi I. But we want to extend want to close it at the very large. So basically this is very large. So that there's the order of the argument, because these poles are extended to infinity plus or minus infinity along the imaginary axis. So you can say that no matter how large this radius r is, you still have some pole outside, right? But for the argument's sake, it doesn't matter. We're just saying that this R, whatever the poles are, will choose a large enough R to include that also. Basically, it becomes a convergence process. If this process is convergent, that then doesn't matter, right? So the idea this loop integral C. Now we add this loop. This is C, right? We add to this big circle. First, we want to argue that this big circle doesn't contribute to the integral, right? And so along so this Z in that case is Z is this large R e to the I theta, right? And R, let R goes to infinity. Right? And then we can consider two situations. One is this exponential function is large, right? When this exponential function is large, basically this whatever the theta range will make the exponential function large, right? So part of this circle, the exponential function will be exponentially large. If there's a real part, that is the real part is R cosine theta. R cosine theta is positive. Then e to the R cosine theta is exponentially large for large R. Then the whole exponential function will be large. And likewise, if it is small, if R cosine theta is negative, then this one will be exponentially small. So there are two situations. One is exponentially large, the other exponentially small. If exponentially large, the whole thing is small, right? Because this is just a power of t. So this exponential function just kill the integral. If the exponential function is small, then it's smaller than 1, so you have just 1, right? So the denominator later is just -1. And then now you look at the numerator at that situation is R. I should say this is t, not this is t. Yeah. The t is t to the e -1, right? So as long as z is less than 0, then this t to the z -1 dt along this line is still 0, right? So that's a requirement for z. As long as the real part of z is less than 0, then the integral is also 0, right? So either exponential function is large or small, the integral will be 0. So by that argument, so this part, you can close the part because this big circle doesn't contribute to the integral. Okay, so that's the argument. So now the argument will be the whole loop is given by the pole of the integral, and then but so this I plus this one is given by 2 pi I times the residue, but this now this is in the negative sense, right? Remember this contour is on the clockwise direction, not the counterclockwise. See that we define it like that. This I sub b. We need to close it this way, go all the way back, and close it, yeah, this way, right? And so the I sub c will be given by all the negative of 2 pi I times the residue. The residue is, let's see, I forgot it. The definition, there's the gamma z. It doesn't matter, it's not included in the integral, but we define it this way. So it's, you have divided by gamma z, and then the residue of this integral, and the residue is sum over in n plus n from 1 to there are two for each n there's two. This is basically plus or minus 2n 2 pi n I, right? Right, for each n there's two pole, and so they are the pole that see the pole that t minus this exponential function e to the 2 pi I, right? 2 pi n I, because the pole is at e. No, sorry. E to the t is equal to 1, t is equal to 2 pi n I. Right? Multiplied by this integral, e to the z minus 1 divided by e to the t minus 1, and take the limit and at actually more space, sum over n, limit of t goes to plus or minus 2. I should say there are two terms. So for this term is 2 pi I, the other term is minus 2 pi I, right? But this term is like that, and then the plus limit of t goes to minus 2 pi n, 2 pi I n, 2 pi n I. T plus 2 pi I n I e to the t plus 1. Right. There are two terms. And now to figure that out, you need to do the basically do an expansion, right? To cancel with this factor, right? It's calculating residue again. Okay. So this e to the t minus 1 when t is close to 2 pi I n, and then e to the t is close to 1, then you can do a Taylor expansion. So this is 1, and then the next term is just t, right? But yeah, the next term is e to the t, because take the derivative, right? E to the t and t minus 2 pi I by n I, right? And then plus the second order derivative, and then t minus 2 pi n I square, right? But this factor in the denominator will cancel this factor, right? And then when t goes to 2 pi n I, this exponential factor is just 1, right? So everything is 1. So this divided by that would be 1 after take the limit, and then t returns to this 2 pi I n and this factor. So let's go continue here. That equals to minus 2 pi I gamma z sum over n of 1 to infinity. Now the first term is this 2 pi n I, that is t, and then z minus 1. Okay, and the second term will be similar, right? Because everything is similar except that there's a minus sign in here. So minus 2 pi I, 2 pi n I minus 1. Okay. And what we will do is would it make it like the relative, I mean, the Riemann zeta function, 2 pi I. I'm just hopefully getting the same as your textbook. So, so your minus, keeping the 2 pi first, 2 pi I, gamma z, and get everything that is not depending on n out, right? And then because you have a 2 pi to the z power, z minus 1 power, 2 pi to z minus 1 power, this 2 pi, so you pull out 2 pi z minus 1 power, right? And you get that and sum over and so if you carry the I, then it's not easy to do it, to make it as a power. The one thing you can do is change this I to the phase angle. So this phase angle is theta is pi over 2. So let's change I. The I here is e to the I pi over 2, right? And then this minus I is over here. So minus I is e to the, combine this minus factor and the I to e to the e I pi over 2, right? And 2 pi we are already out here. So there's a phase is it's become 2 pi I pi over 2 z minus 1. This becomes 2 pi I. 2 pi 3 I pi over 2 z minus 1. All these are not depends on n also. So the n is only n to the z minus 1, right? And n to the z minus, both are n to the z minus 1. So it's n to 1 minus z. Okay, everything depends on n is here. And the rest is the 2 factor e to the I pi over 2 minus 1 and plus e to the e pi I over 2 z minus 1. Almost there. Okay, so all these are just phase, right? All these are just phase factor. But the important thing is this one. If you compare with the definition of the Riemann zeta function, is the argument of the zeta function is this power of this n. So now the power of n is 1 minus z. So this whole thing is gamma 1 minus z. Right. And the rest is so there's a phase factor. You have all this power of z, 2 pi to the z, and then all this phase factor involving z in the argument. So this is essentially 13.65, right? 13.65, 2 pi c gamma c, except that you can put this minus I also into the phase factor, basically changing the two phase factor, because there's a minus 1, right? So this gives you a e to the minus I pi over 2 is minus I, right? This factor gives minus I. This one is 3 pi I over 2 is in the negative sign. Negative sign will give you I. This one will give you I. This one gives you minus I. And so you multiply minus I here. And it gives you a minus sign and then a positive sign here. So basically flipping this and changes to a negative sign. Okay, so that is, you take that into account. Let's just write it on one more line. So this would be your textbook formula. 2 pi to the z. You cancel this 2 pi with this minus 1. So 2 pi over z. And then this is e to the 3 pi I over z over 2 minus e to the pi over 2. Okay, this is 13.65. So it took a while to derive that. It's not totally done, but at least you see from up to here, you see the reflection. So the zeta c and zeta 1 minus c are related to each other, right? So if you have a z, say if this formula extended to the say 1 minus c, if 1 minus c is greater than 1, if 1 minus c is over here, then if 1 minus z is greater than 1, then means the z is less than 0, right? The gamma z, yeah. So this equals to this equals to that. Gamma z will be less than 0. So whatever you have originally defined here, and now you can reflect it back to here. It's not a total reflection because you have all these other factors. So gamma z and gamma 1 minus z related to all these phase. There's a phase factor here, there's a phase factor here, and then there's a gamma function here also. It's not totally reflection, but they're related to each other. They kind of reflected to z less than 0. And the refraction line is when the two are the same. So here's when 1 minus z equals to 1 minus z, right? Z. If z equals to 1 minus z, that means z is 1/2. So the reflection line is at this point. 1/2. Meaning that if you have a 1 minus z, is the real part is at z equal to 1/2. This would be 1/2, and this would be 1/2. You don't get anything. I mean, you can have an imaginary part different, so you can reflect it from the other way around. So if you have a positive imaginary part, and this will have a negative imaginary part, that's a reflection. But as long as the domain with respect to real z, you don't change anything. If real z is 1/2, then you still go back to real z is 1/2. So this line is a reflection line, and this is a special line. Okay, and so this is 13.65. It's not done yet. There are a couple more steps, right? And which you use the reflection formula in the the gamma function, remember the gamma function has the reflection formula. If you forget, I can point it out to you. The reflection formula is 13.23 or 24. It depends on how you want to use it. 13.23. And then there's a duplication formula, 13.27. And now the rest is just using those, the gamma function reflection formula for this gamma function and the duplication formula to write it in a little nicer form. But I've already spent enough time, so we'll just quote your textbook form. It's just a little bit algebra to. The rest is not tricky. It's just use those two formulas to relate. We have to call this one. Okay, so basically, this is just intermediate step. All this. So finally, if you use those formula and you can divide this a little bit more symmetric form. The 13.67. So basically, it's still related gamma z to the gamma 1 minus z. Not gamma zeta z and zeta 1 minus. Yeah. Now the reflection formula is like that. This is a pi over 2 zeta z. Okay, and that is equals to gamma. Let's see, over 2 minus 1. Yeah, over 2 zeta minus. Okay, so essentially the same formula, except that you're just using some property of gamma function to write it nicer. Okay, so it's relating to, again, relating gamma at 1 minus z to gamma z. So that's that kind of important. So using that, you can now extend, because we already did that, the domain actually using the Dirichlet series, you actually extend it to here, right? All the way to z greater than 0. Now you use the reflection formula. So by this reflection, you can actually extend it to all the way to z less than 1, real z less than 1. So you cover the whole complex z plane. Now the Riemann zeta function is defined over the whole complex z plane. So that is nice. Okay. Then and over the whole complex Z plane, we already mentioned that using the Dirichlet series formula, we know that at z equals 1, there's the only pole of the Riemann zeta function at z equals 1. So there's a pole at z equals 1. Other than that, it's analytic. Okay, and that actually gives you the formula that relating gamma 0 to z equal 1. If you I should say if yeah, I should say for gamma 0 and gamma 1 are related. If you use the reflection formula, that gamma 1 is singular, but gamma 0 is not necessarily singular, because for z equals 0, the gamma function gamma 0 is also singular. So both gamma function and the zeta function is singular. This turns out the singularity cancel. The gamma as 0 is actually finite. Okay, so actually the next two formula, the textbook divide the residue of the Riemann zeta function at 1, which is pretty straightforward, just using the simple pole formula. And then using this formula to relate it to gamma 0. And then again, take the limit, then you can show that the gamma 0 is minus 1/2. So it's not singular because I used the original summation formula. It doesn't include this form, and even the integral formula doesn't including z equals 0. Right? If z equals looks like it's z equals 0 looks like it's, you set the set to 0 is divergent. Right? And also the Dirichlet formula also not give you this value. So this value is given by this reflection formula. Okay, so those two straightforward, you can derive this the residue and the 0 value gamma at 0 quite in a straightforward way. Right. Okay. So I won't go to that because it's already taken a long time. All right. Now up to here is okay. So this is just basically for your knowledge, and to divide that is basically get to a sense that why this line is so important. The z equals 1/2 line is so important because this is how you reflect the gamma, the zeta function, and make it cover the whole complex plane. So that's the special role this z equals 1/2 line is playing.